UESI has provided nuclear diving services in the U.S. and Asia for over 30 years. UESI divers work in the suppression pool, spent fuel pool, reactor vessel, and a variety of tanks. Commercial nuclear plants have adopted this approach, often in lieu of robotics or drain down, and have found that it typically reduces dose, cost, and schedule. Numerous case studies are available that support this. The utility and viability of intervention by divers in decommissioning work can be summarized as follows. Divers can work efficiently because they are very mobile and able to get close to the work. This allows them to work quickly and accurately even in turbid conditions. Divers eliminate the need for dewatering and scaffolding. Divers can work close to high radiation sources because water affords an extremely effective shield, and the inherent efficiency of diving reduces stay times. The use of commercial dive equipment and careful attention to procedures prevents skin contaminations, even in highly contaminated water, and also protects the diver from the other hazardous materials that may be present. Diving procedures and equipment are simple and reliable, promoting excellent productivity. Off-the-shelf tools are typically adaptable to underwater work. This includes most pneumatic and hydraulic tools, as well as thermal cutting equipment. The decommissioning tasks that divers perform and are well suited for include sludge removal, debris segregation, packaging and removal of small and large highly radioactive debris, rapid segmentation of large components, concrete scabbling, and application of underwater coatings to fix contamination prior to dewatering. Divers can support simpler and more cost-effective remote tools. While diving is an accepted maintenance practice in all U.S. commercial nuclear plants, as well as many other plants around the world, it has been utilized in D&D work less frequently. This appears to be because the perception is that it is low-tech, inefficient, and high-risk. Though the first point is true to an extent, it has proven over tens of thousands of dives to be neither inefficient nor high-risk. An alternative to a pure diving approach is to combine the use of divers and remote tools. Divers can assist in the installation and operation of tooling, allowing for much simpler and more cost-effective tool designs. The following examples exhibit typical ways in which divers have been used to support decommissioning work. Large component segmentation. A combination of divers and remote tools can be used to efficiently segment large components. The following animation illustrates how this process works on a steam dryer. Once the dryer is placed in the DSP, divers assist in the installation of a track system used to make large cuts in tight and/or high-dose areas. Once the track system is in place, the diver can exit the water or move to a low-dose area during the cutting process. After a cut is made, divers reposition the cutting system and are also available to perform maintenance on remote tooling as necessary. For cuts in locations accessible to divers but difficult for remote tools to access, handheld cutting tools can be used to make the overall process more efficient. Working in tight spaces. Working in close quarters can be difficult. Designing remote tools for this purpose may be impractical or prohibitively expensive. The following animation illustrates use of divers to sever and remove the internal components of a steam generator so that the steam dome can be separated from the lower unit without breaching the steam tubes while keeping the process within ALARA goals. The crowded spaces within the steam generator afford minimal working room. Dose rates are also very high. In order to facilitate entry and provide a low-dose working environment, the steam generator was staged horizontally and flooded. Divers were able to enter the lower assembly in the space adjacent to the steam tube bundle shroud to make the circumferential cuts necessary to separate the steam dome from the lower assembly. Two parallel cuts were made around the full circumference of the shroud. The section cut from the shroud was then cut into smaller pieces that could easily be handled by divers for removal from the steam generator. Divers cut an access hole in the shroud and then entered the steam dome to segment the two bundle support beams. The final cut to separate the steam dome from the lower assembly was made externally. Segmentation of smaller high-rad components. Divers using cutting tools and long-handled extensions are able to segment high-rad components while receiving minimal dose. The following animation shows a diver working in the fuel pool near a pipe section reading 1000 millisievert, or 100 rem per hour. A pneumatic reciprocating saw can be quickly attached to the pipe, limiting the diver's time near the source. A major advantage that divers enjoy is the fact that water is an extremely good shield. Dose rate is cut in half for every 18 centimeters, or 7.2 inches of water, between the diver and the source. This allows divers to work very close to a high radiation source. For example, the effective dose rate from a 1000 millisievert or 100 rem source is reduced to 0.01 millisievert or 0.8 millirem at a distance of 3 meters or 10 feet. As the diver moves away from the pipe, the dose rate drops from 100 rem per hour to 0.01 millisievert or 0.8 millirem at the end of the long-handled tool. The diver actuates the saw using the long handle to make the cut while in a low-dose area. Using underwater coatings to fix contamination. 100% solids, two-part epoxies can be applied underwater to seal contaminated steel or concrete surfaces, as well as to stop leakage. The coating cures underwater in 12 to 24 hours and prevents the spread of loose contamination or airborne contamination. Prior to coating application, excessive loose material can be removed by hydrolasing or laser or mechanical scabbling. A vacuum system is attached to capture and filter loose particulate. Two-part epoxies can be applied efficiently using a plural component pressurized delivery system and roller applicator. The resin and curing agent are mixed at the tip and delivered to a specially designed roller applicator. Various types of end effectors can be attached for leak sealing purposes. The diver is able to control the flow of coating to the roller as it is applied to the surface. As the coating is rolled onto the surface, water is displaced and the coating clings to the substrate. The cured coating produces a highly durable, tightly adherent barrier that prevents the release of contaminated particulate from the underlying substrate. The coating also prevents the corrosion of steel substrates and may aid in stopping or preventing minor leakage. The suit is made of highly vulcanized rubber material that is completely watertight. The material is very resistant to abrasion and puncture damage. Steel-toe safety boots are made as part of the suit. Divers' radiation gloves attach to the suit with hard rings at the wrist cuff of the sleeves. 2 pairs of gloves are worn and each is sealed separately. In addition, work gloves are worn over rad gloves to prevent damage to the gloves or the seal. There are watertight wrist seals beneath the gloves so that in case of a glove leak, water cannot enter the suit. The suit is pressurized to keep water out. Under the suit, the diver wears the same protective clothing worn by all other radiation workers. In the unlikely event of a suit leak, the anti-contamination clothing would prevent direct skin contamination. The diver helmet seals to the suit at the neck with a watertight O-ring seal. The helmet is mechanically locked in place. The intake and exhaust valves on the helmet are specifically designed for nuclear diving to prevent any water entry. During diving, air is always flowing to the helmet to maintain a positive pressure and keep water out. Air hoses are connected to the diver helmet with screw-on fittings and cannot disconnect on their own. Only one connection point will be underwater. Hoses are pressure tested to ensure they are safe and are always pressurized to prevent any water entry. The diver helmet and dive suit are leak tested before each dive. An in-water leak check is also performed as the diver begins his dive. During the diver continuously checks for any leaks. If any small leakage is suspected, the diver will quickly leave the water. The diver can be removed from the water within 1 to 3 minutes. During the diver is continuously monitored for radiation exposure by teledosimetry. The dive control personnel can see his radiation dose rate on a computer at all times and can also monitor his total accumulated dose while diving. In addition, divers can be monitored daily by bioassay for any possible internal uptake. When the diver leaves the water, his suit is checked for contamination and dose rate. He is decontaminated while still in the dive suit to remove any loose contamination from the suit or helmet exterior. The suit is then carefully removed, and the diver removes his protective inner clothing as he exits a contamination area. He is once again checked for any contamination. All personnel are carefully trained in these procedures. An experienced dive supervisor continuously monitors all aspects of the diving operation. Using these procedures, UESI has performed thousands of dives in contaminated water without a serious incident.